Congratulations on completing the last task and on generating 10 values for the sample mean. The code you generated using the blocks should have looked like something like the code shown on the left of the slide here. In the code shown here, this function generates each of the sample mean values, while the code at the bottom ensures that the function for generating the sample mean is run multiple times and that a set of samples are thus generated. When these samples that are generated are plotted, you would have observed something like the graph shown at the bottom of the right of this slide. The 10 values for the sample mean are not identical, which makes total sense. Each of these sample means is a random variable. Each of them is computed by adding together uniform random variables, so it should come as no surprise to find that the final value for the sample mean is also random. How, though, does this observation that the sample mean is random fit in with what we know from the law of large numbers? Remember that the law of large numbers tells us that when we sum a large number of identical random variables and we divide this sum by the number of random variables we generated, we get the expectation. Surely then, we might argue, that all the sample means we compute should take the same values, namely the value of the expectation of the distribution. What we need to remember, however, is that the law of large numbers only holds in the limit that we generate an infinite number of random variables. If the number of random variables from which we compute our sample mean is finite, we get a number that is close to the expectation, but that is not exactly equal to the expectation of the distribution. We can thus reconcile what we know from the law of large numbers with what we observe in this graph. The 10 estimates for the sample mean are all different, but all of them have a value that is close to the expectation of the underlying distribution, which in this case is 0.5, as we are sampling from a uniform random variable between 0 and 1. With an understanding of these ideas behind us, we are thus in a position to get onto the content of this video, which is about a computationally cheap method for estimating confidence limits. Let's start by briefly reviewing what we have done to compute these confidence limits in previous exercises. In essence, we have always used a resampling strategy like the one illustrated in the code on this slide. This code works by running the code to calculate our sample mean multiple times. We thus extract a sample of sample means and extract summary statistics from the distributions for this sample. There is another way, however, and this new way relies on the central limit theorem. This theorem is shown on this slide. The expression shown here provides a relationship between the distribution we are sampling from when we compute a sample mean and the probability distribution function for a standard normal random variable. Let me reiterate, the central limit theorem provides an analytic expression for the distribution that we are sampling from when we generate sample means. In the rest of this video, we are thus going to see how we can exploit this analytic expression when computing confidence limits for sample means. Before we get onto that, let's have a look at the analytic expression for the distribution function for the sample mean that is shown on this page in more detail. The expression shown involves the probability that the random variable is less than or equal to z. It is thus an expression for the cumulative probability distribution function of the random variable. To be clear, this is the form of the central limit theorem that you should give if you were asked to state this theorem on an exam, as it is a mathematically rigorous way to state the result. Personally, however, I find it easier to understand the significance of this result once I have used this expression to derive an expression for the probability density function for my sample mean. The expression that you get once you complete this derivation is shown here. To be clear, S over n here is the estimate of the sample mean once more. N is the number of identically distributed random variables from which the sample mean was computed, and mu and sigma squared are the mean and variance for the distribution from which the identical random variables were generated. Hopefully, the right-hand side of the expression at the top of this slide is familiar. This is just the probability density function for a normal random variable with expectation mu and variance sigma squared over n. This familiar bell-shaped curve is shown at the image on the bottom right of the slide. The central limit theorem is therefore telling us that the distribution we are sampling from when we compute a sample mean by taking the sum of a set of identical random variables with expectation mu and variance sigma squared is a normal distribution that is centered on mu. Furthermore, as the movie shows, the width of this distribution narrows as we increase the number of samples that we use to compute our sample mean, because the variance for the distribution of the sample mean is sigma squared divided by n. This is certainly a cool result, but the question is, how do we use it to get our confidence limits? The answer is that we assume that by calculating our sample mean and sample variance, we have calculated the parameters for the distribution of the sample mean. The central limit theorem shows, after all, that sample mean is just a sample from a normal random variable. What this assumption means in practice is that we are assuming that if we were to calculate more sample means, what we would essentially be doing is sampling from the probability density function shown on this slide. We'd be sampling from a normal random variable that is centered on the value of the sample mean, mu, and that has a width that is equal to the square root of the sample variance, sigma, divided by the square root of the number of samples that we generated to compute our sample mean. Because this curve is a probability density function, we can extract the probability that our random variable, our sample mean, will take a value between two points, lower and upper, by integrating the curve between lower and upper. To extract our 90% confidence limits, we thus need to set the values of lower and upper so that this integral is equal to 0.9 and so that mu is the midpoint for our integration range. The values for lower and upper will then be our confidence limits. The way that these confidence limits are determined in practice involves using the cumulative probability distribution function for the normal distribution once more. If lower is set to the value where this function is equal to 0.05, the probability of our normal random variable takes a value that is less than lower is 5%. Similarly, if upper is set to the value where this function is equal to 0.95, then the probability that the random variable takes a value that is larger than upper is 5%. In short, the central limit theorem ensures that we can calculate confidence limits on our estimate of the sample mean by just looking up numbers from the statistical tables. If we have access to a computer, it is even better, as the computer can do this looking up for us, as there are functions we can call on that do the process of looking things up in the statistical tables for us. The process of calculating the statistical errors can be made even simpler by exploiting the derivation that is explained in my other video on the central limit theorem. This derivation proved the following relation between the level of statistical confidence PC and a quantity epsilon, which measures either the sample mean minus lower or upper minus the sample mean. To summarize then, what I hope you have gleaned from this video is that the central limit theorem tells us the distribution that we are sampling from when we calculate a sample mean. We can thus extract the parameters of this distribution from our samples and can compute confidence limits relatively straightforwardly and with little computational expense. This is precisely what you will need to do to complete the next task. So as always, good luck.